Today's lesson is on direct and inverse variations, not to be confused with finding the inverse function. This is different. So first of all, let's look at a direct variation, and it would be read like y varies directly with x. This is a linear function. Okay, it's always linear, and furthermore, the y-intercept is always 0. Notice that. The y-intercept is always 0. So it's always going through the origin. Okay? That's what it looks like graphically. Also, k is a constant represented by any real number. Okay? Any real number. Now, for an inverse variation, it would be read as y varies inversely with x. And notice that our constant is still k, but now x is in the denominator. Inversely means x is in the denominator. That's very important. And this is going to introduce us to a new type of function called a reciprocal function. And we're going to talk about how to graph that at the end of today's lesson. This is a reciprocal function, and we're going to find that reciprocal functions have asymptotes, and we'll talk more about what that means. Okay, let's just jump right in and see what the difference is between a direct variation and an inverse variation. And many functions are neither. Okay, in order to do this, let's look at the two models we have here. Notice if x is in the numerator, it's direct. X in the denominator, it's inverse. And we'll notice a couple of more things. So A definitely is an inverse. You can see we have a constant. That would be 3, and that x is in the denominator. Here, x is in the numerator, and our constant is k. So we say that this is a direct variation. This one has an intercept other than 0, so this would be neither or neither. Here, at first, it doesn't look like either one, but if we were to divide both sides by x, we would get y equals 4 over x. And now we can clearly see that this is an inverse variation where k equals 4. Notice on part B, k was a fraction, and that's totally okay. K can be any real number. If we look at E, because we're adding something to the x, this is a neither. Now, what if we don't have the equation and we just look at it as a table? I can see that x times y equals 24 for all of these, okay? So look at what's going on with the numbers, and then of course we can divide by x, so we get y equals 24 over x, and now I can see that this is an inverse function. But let me give you a little shortcut, okay? When you're looking at a table, okay, so from a table, if you have constant products, like we just did, all of the products were the same number. If that's the case, it's an inverse relationship. So constant products signify inverse variation. But something different happens down here, looking at this table. We have 3 over 4 is 0.75. And notice 6 over 8 is 0.75. So when we divide x by y or y by x, we get what's called a constant ratio. So if you have a constant ratio, this is a direct variation. And most of you are a little more familiar with direct variations, as you'll see. This one would be very easy for us to write a formula because x divided by y equals 3/4. And if I multiply both sides by y, we get x equals, oh, I want y by itself. I didn't do that quite right. Let me get y by itself. So at this point, if I multiply both sides by 4/3, that's really messy. Oh, Miss Adams, this is 4/3 x. So that's really messy, but that would be a quick way to write that as a function, which I didn't ask you to. I just want you to realize that this is a direct variation, and the reason that it is because we have constant ratios. Okay, the ratios are constant. Okay, let's move forward. Here's something that I'm definitely going to ask you to do on your upcoming, or on your next test, I should say. If y varies inversely with x, so the first thing we know is that we're working with an inverse variation. And x equals 4 when y equals 5. Then write a function and then find y when x equals 2. I've given you a few steps. Some of you have expressed that you love the steps, so here you go. The first thing you're going to do is pick a model. Since this says it varies inversely, we're going to pick the inverse model. So we're going to start with y equals k over x. And now we're going to take the information that's given and figure out what k is. So I'm going to plug 5 in for y, and I'm going to plug 4 in for my x. And now it's easy for me to solve for k. K equals 20. So now we've solved for k. Now we can substitute k back into the model. So now I know k is 20. So y equals 20 over x. That's my model, and that's the answer for part A. Okay, so that's my answer for part A. That got weird. Alrighty, now for part B, it says find y when x equals 2. So find y when x equals 2. We're just going to plug 2 in, and we see that y is 10. So that's our answer for part B. Alrighty, for example 3, we're going to do the same thing where we're going to write the function and then we're going to find y. Okay, so y varies directly. So the first thing we know, because this is a direct variation, I'm going to pick this model, the direct variation model. And then I'm going to solve for k. So I'm plugging in 8 for y and 3 here. So to get k by itself, I'm going to divide by 3. So k equals 8 over 3. Plug that back in for k. And so now my function. Alrighty, and for part B, it says find y when x equals 6. So y equals 16. Alrighty. So that's pretty straightforward, and that's about as hard as it gets. The numbers can get nastier. You know, what if x were a radical 3 or something weird? But the concept, that's as hard as it gets. I'd like to show you a little bit on how to graph reciprocal functions. So for y equals 1 over x, go ahead and pause and fill in this table. If I plug in -2 right here, I get 1 over -2. If I plug in -1, 1 over -1 gives me just -1. But notice what happens if I do this. This is really saying 1 divided by -1/2. And remember, when you divide, that's the same as multiplying by the reciprocal. So we can see we simply get -2. What happens if you divide by 0? It's undefined. And this is the same as this one except for the sign. So you'll notice that the values seem to repeat except for their opposite. Now let's plot these points. -2 goes to -1/2. -1, -1, -1/2. By the way, I only gave a few points, but what if I went to -1 over 10? Then this would just be -10. So the closer I get, this shoots down really fast. You know, it just, as well, if I go to -40, that would be -1 over 40. So I would just get super close, but never touching. Okay, never touching. Oop, just closer and closer, but never touching. And when we plot the points, and how do you plot undefined? That looks just like an asymptote, okay? So when x equals 0, we have what's called an asymptote. And you're going to find also that we have another asymptote. Asymptotes, let me make sure you know how to spell that. These are what I like to call limit lines. Okay? Asymptotes are like first dates. You get close, but you don't touch. Okay, let's continue on. If I graph this point, 1/2 goes up to 2 and so forth. And you're going to see the same thing happening here, where you just get closer and closer both ways. This is a function you'll study a lot more in pre-calc. This function is in 2 separate pieces, okay? So for this function, we say that it is discontinuous, okay? And later you'll look at limits and see all types of nice things that happen with functions like this. But right now, this one graph is in 2 separate pieces, but it is still one graph. Now, for example 5, I'd like to show you some transformations. An easy way to do this is to go opposite here, same, opposite, same. And you're familiar with that technique. We're going to go to 4, 2, and you're going to put a point. And now you're going to make your asymptotes go through that point, 4, 2. And now we can mimic what we did here. Over 1, up 1. Okay? Same thing. And, we can fake the rest. Hopefully you're okay with that. And you just go through here and here. And notice we have the same graph except for a couple of shifts. Okay. Opposite of the one that's next to the X and the one that's on the outside, you keep it the same. Now, what happens when the numerator is different? Let me show you what happens. If I plug in -4, I get a -1. -2 gives me a -2. 4 over 0 is still undefined. And 2 is also undefined. 4 over 4 is 1. So if we plot these points, -4 goes to -1, -2, and 4, 1. Notice that this graph is pulling away from the asymptotes in the middle, okay? And again, we still have the same asymptotes. Notice there's nothing here, nothing here. And these are always mirrored. Okay, so if that's a 4, 4, 1. Okay, if that was a 7, I'd go 7, 1. Alrighty, so that's really easy. And you're going to notice, let's say you had negative and you wanted to graph that. Instead of being in the first and third quadrants, you'd be in the second and fourth quadrants. So we just flip it. And we'd go 1, 1, over 1, down 1, because the numerator is 1. So our transformations, you're noticing they still work the same way.